Hi everyone. So I actually wasn't listening to the introduction, but I think you mentioned I work for OpenAI. We're okay, got it. We are a research nonprofit located in San Francisco, and for the last a while, I think almost a year, I was working on a project where we are building a bot that plays a game called Dota 2. Dota 2 is a massively popular online video game. And what I'll try to do in this presentation is I'll try to give you an overview of how would one go about building such a bot. And I'll try to give you just enough information for you to be able to judge for yourself if the techniques I'm going to be talking about, some of them which proved very powerful in our work, is this something that you could use to tackle your own problems? Dota is being played with reinforcement learning. And reinforcement learning is a branch of machine learning, and it deals with control problems. So here you have a couple of examples of control problems. Two of them are video games. So you have Sonic the Hedgehog up in upper left. Bottom left is our own work on Dota 2. Then you've got some self-driving situation here in a kind of simulated game environment, and also robotic manipulation by like a robotic hand that does something. So in a reinforcement learning setting, you have agent and you have environment. And these two interact with each other. Agent, you can think of it as a function. It takes in some state and it says, what action do I do in this state? So it's a state, or it can be observation. We say observation if it's not a fully observed situation. So what does it mean? Let's say I'm building a bot that controls a robot. You know, if the robot is like walking around over here, you know, it doesn't know what's behind it, for example. It's just like looking out of the camera. So, you know, it doesn't know, you know, the spin of every atom in the universe, because like that's the environment it operates in. It just has some observations, which are cameras and sensors and these types of things. And then environment is what keeps that state in, you know, in our little abstraction over here. And it takes action from the agent, and it kind of like updates, you know, what happened next, and it provides state again to the agent. And then we have a reward, and reward is what actually defines the reinforcement learning problem. So when you think about it, like let's say I want to build a robot that, you know, walks across this room. I will give him a reward for getting right there. There are like different ways to do it. One way would be it's not going to get any reward until it like reaches the end of the room. The other approach would be the closer it is getting to the end of the room, it's getting more and more reward. So it has kind of like this path laid out for it, so it can like quicker get that like, oh, you know, I'm learning to do something better. And here you have another example. So it's a game of Sokoban. Who didn't play Sokoban over here? Oh, okay, we've got a few people. I'd rather say, you know, who didn't than who did, because there are always some people who like just never raise their hands. So a little inflated over there. So here the agent would be this like function, program, you know, whatever you call it, that takes the board of Sokoban and says, oh, you know, with this board, I'm gonna go right. And environment is kind of like the game itself, like the program that you would be playing with on your computer that says like, okay, you press, you know, the arrow right, so I go to like this next state over here, and like for now you get a reward 0. And then, you know, like in the other case, kind of like you say, okay, like in here I'm gonna also move right, and you know, you reach some final state and you get reward 1. And excuse my scribblings, I'm actually recently introduced to Apple Pencil, and I'm really enjoying it. So the reinforcement learning solution is that it will collect what we call rollouts. So rollout is this series of state, action, reward, state, action, reward, state, action, reward until like the end of the episode. In this case, until the end of the game. Also, what agent is trying to do in its training, it is trying to maximize not the next reward, but like the whole sum of rewards going forward. So what we will collect is there a pointer here? Is this, oh, it's a pointer. Yeah, so it will calculate returns. And return is basically a function of reward now and like all the rewards to the future. It could be just some of them, or like maybe a sum that like favors short-term rewards, and like if it's far in the future, maybe it's like a little bit lower weight or something. And then we have these triplets, state, action, return, state, action, return, and we basically know that like if I was in this state and I took this action, I got this return for the rest of the episode. So we will, in our training, basically try to encourage whichever action was good for us, whichever led to high return. Yeah, and in most cases, like these will actually become obsolete as we keep training, because this deals only with the next action. So when the agent gets better and better, okay, we know that like from this state, we took this action and we got this return, but we don't know anything about the future actions. So with the better agent, we're probably gonna get better returns. There are also some interesting failures over there. Failures are frequently actually related to how we define our rewards. So here's, okay, no, stop. Here we go, first one. So this is a game called Coast Runner, and the goal of the game is to race your boat like around the track, and like you get some points for that. And here the agent actually discovered that you can also get like some reward for collecting these like little green things over here. And it actually decided that like it makes more sense to make this perfectly timed circle around the middle of the track and keep collecting these green things as they respawn. And it can actually like get more points by doing that than like actually racing the game. In this other case over here, we have a robot called Fetch. It's a simulated one. And it's supposed to push this green puck towards the red goal, except that it realized that if it doesn't get it perfect, it can actually go ahead and move the table additionally afterwards to just like get it exactly there. So one more a little theoretical thing, and I'll show you some videos over there. But there is a big problem in reinforcement learning. It's called exploration. And the deal with exploration is that like it's a collection of techniques that we use to encourage seeing these like good states. Because usually we start with an agent that's just completely random. It's like flailing around, and then it has to see those rewards in order to know like which actions it's supposed to encourage. So here's a very theoretical game. The green squares here are good. You can walk around them. Red squares are like sudden death. End of the episode, you get 0 reward, go back to the beginning. The little guy is like what you control. And then you've got the diamond, and if you get to the diamond, like you win the game and get some points. So here, you actually, for like the random agent, you actually need to make like to the order of like 2 to the power of n episodes or games just to see random agent reach the diamond once. So it's pretty tricky. Like if this board is like pretty long, then like you can train forever and like only see this couple of examples where you get like any reward whatsoever. So what are good reinforcement learning environments? Like ones where reinforcement learning can like really help you deal with it. The starting random policy needs to be able to find interesting trajectories or rollouts, you know, like the games where, you know, you get rewards in like different ways so that we know which actions to encourage. There has to be possible gradual improvement. So, you know, what I just said, it has to be also true for like later stages of the game. If you play a little bit, you learn like your agent to do something a little bit better, and then you're in some state, and you know, whatever you do, there's like a big leap forward you have to do that is like really hard to, you know, not randomly, but like at this level of the agent to stumble upon this like additional rewards. So there has to be the possibility for gradual improvement. Now, reinforcement learning is really, really data intensive. So you have to frequently train a lot and generate a lot of data in order to be able to like get end results. So your problem, ideally, there are examples of applying it in the real world, but ideally it should be either virtual, such as, you know, a video game, but it could be something different. It could be something like stock trading. It could be something like delivery management. It could be something like, you know, although this is more like simulatable, but it could be something like you know, managing the power in data centers, like DeepMind did, right? Or it has to be like simulatable. So robots are also a very popular use case where there's like a lot of training happening in the simulators, and then people move it to the real world. Or self-driving as well would be one case. And finally, from the research perspective, we want to pick environments which are just interesting, which will lead to interesting behaviors of agents. So self-play is a technique that we found very powerful in our work. And the idea is that like we start with a very simple environment. Here, like you have some examples of environments that started off as like this area, and we would have this like little ant or something, or little humanoid, and they were supposed to just like learn to move around. The agent would be actually controlling their muscles, and you know, it would be a challenge just to like move around. But then if you want to make it more complex, once you like learn to move, you actually as a researcher have to go and like manually say like, oh, you know, I'm gonna add an obstacle that like, you know, you have to like jump over, or like, you know, I'm gonna add something that you have to pick up or whatever. And here the idea is that like we start with this simple environment and pit two agents against each other. And as one agent is learning to perform better and better, the other one is as well, because it's basically a copy of you. So you get this like really cool like automatic curriculum. Like you always have to beat somebody who's like getting better as well. And I have some examples over here for you. So yeah, here we see like two agents that are trying to like push each other off this this little round thing, like little sumo. And like they actually, you know, they look kind of funny, right? Because they're not, you know, their muscles didn't evolve or they weren't meant to, you know, like ours to like minimize energy usage, you know, walking around in the real world. They were basically kind of like taking from humans and put like in the simulation. You know, and that's even more true for like this like little creatures over here. But you see this like behaviors that like we could relate to. Like the previous guys like learned to like tackle and these kinds of things. And here you're trying to score a goal. I think it's always more appreciated on this side of the ocean more because we don't have a version for American football of this. But yeah, you can see kind of like, you know, the defender kind of like moving, moving in response to like where the opponent is going, and like, you know, it kicks off its leg to like try to defend. And like here, the agent is supposed to basically just like try to cross to the red line, and the other one is like trying to prevent him from that. Yeah. So with this, I want to move over to like our Dota 2 work. So Dota 2, as I mentioned, it's a very popular video game. The idea is that like it's on this map over here, it's like 5 players playing against 5 other players. These are their bases over here, and there are like 3 lanes through which where like most of the action is happening. What do we have? Each player chooses a hero. These heroes have unique abilities, so like some of them can like counter the other, and so on. And then the goal is to destroy enemy ancient. Enemy ancient is like this building inside of the base at the end of the line. And our approach was to try and beat the best humans out there, no matter how. So like, like we didn't set off saying like, okay, we're gonna go and like discover new reinforcement learning algorithms over there. We wanted to say, you know what, like if we can like make good scripted bot and like that's already gonna win, that's fine. But possibly we'll probably have to like end up with like reinforcement learning, and we'll probably try to like use AI to beat the game. And the funny thing happened was that like we started with this best possible scripted bot, and one of my colleagues went off and spent like 2 or 3 months and like just like worked on it all the time, and basically emerged with probably something like the best scripted bot for the Dota 2 so far. And then we built this like limited version of the game to make it easier for reinforcement learning to learn initially. And then we built like the initial framework and trained it for like a little bit. And then with this like still a lot of bugs in it and everything, we pit it against the scripted bot, and it just like destroyed it. So it's like a huge validation that like, okay, like, reinforcement learning is actually a way to approach it. And like, why Dota 2 at all, or like games at all? These are environments that are very complex, but at the same time, they are very easy to simulate. In few steps, you can get interesting behaviors. For example, if you're trying to teach a robot, it takes actually a lot of effort even to like stand upright. And like here, it's not a problem. And then you can learn like short time horizon tactics, where like, you can be confident that, okay, for AI, it should be easy to learn that kind of like if you have like a couple of units around that, maybe like you have to, use the back one to shoot the front one or whatever. Like I don't actually play the game, so I don't know how these tactics actually work. But, like you should be able to learn it. And then the big question was, can they learn this like long-term strategies for the game as like you build up throughout the match towards doing something? And then we wanted to study deep reinforcement learning at scale because with these like deep networks, we can't really interpret all the individual decisions. But maybe we could learn something from like where these decisions fail, or maybe we could learn, maybe we could see them add up these decisions to like long-term coherent strategies. So I think we're like slowly running out of time. So I'm just gonna play, okay, maybe I'll skip the video then. I'll just go to some closing thoughts. And some of the applications of this kind of like deep learning and AI right now are not very economically useful right now. So like you might question like, why are we even like doing it? But the role of the research organization is like not necessarily providing you with a product. We are trying to push these AIs to go as far as possible, and it's kind of like up to industry to decide, is this technology like ripe for picking? And I think in many ways, RL is already being used out in the industry for things like, like route planning, stock trading, warehouse management, all kinds of things like that. And it's just going to grow and grow and grow. It takes a lot of compute to train these things, but here's the thing. One, it takes a lot of compute to train it, but then to run your model, it's like very little. And then two, it takes a lot of compute to train it for the first time. So because with AI, it's like really hard to tell, like, if something is not working, why is it not working? Maybe you just have to like add a bunch more, computers, like 10 times as many GPUs, and maybe it's just gonna magically start working. So you end up like throwing all of this like compute available at it. And then like, once it works for the first time, you discover like, what, like I recently fixed some bugs and like, sure, I added this compute, but maybe we can like cut it down. And frequently it turns out like, what, I can like divide like my compute budget, by 10, and like it's still working. And then there are like fascinating ways in which reinforcement learning explores. We definitely seen it in our work, and I guess I didn't have time to like show you the video, but like you can see it by going on our website. And like here, I also included the game that Joanna mentioned. This is the AlphaGo game against Lee Sedol, and I also don't know Go at all, but move 37 over here by AlphaGo was apparently very surprising to experts. So because like the thing is that the reinforcement learning ends up making every possible mistake many times over. And like, what, like sometimes it's just gonna learn not to make it. And like we humans would have learned quickly, like not to make it. But like sometimes it's like, discovers like one move or like one thing it can do about it and just like find completely different path. So with that, thanks for listening. You can visit our website or Twitter to like learn more.